In this example, we're ultimately just going to look at a simple beam situation, and we're going to apply the moment area method to perform some calculations on deflections. And for instance, what we want to find out is what the maximum deflection is in the beam under a peak live load kind of situation, right? And do some comparisons related to that. Now, the building that we're looking at is this multi-story steel frame building. You see the partial framing plan down below. We're only going to look at this particular beam, right? So it has then some joists that frame into it. That's going to create point loads on that beam. We're going to, because of the magnitude of those, ignore the self-weight of the beam itself. We can easily accommodate that through other means, but remember, this is a live load only kind of situation, and that live load is 60 psf as an average of the corridor in the office space. We're only going to look at those effects of those temporary loads in terms of the deflection of this particular beam, which is a 16 by 31. Right? So from that, we do a tributary area type analysis, and it starts to lead us to this kind of view. Here we got the two columns. This is the elevation view. Here's these other joists that are framing in, from which then we get the reactions of those become point loads on the beam. That these are spaced at 7 foot 3 inches on center for a 21 foot 9 inch total span. Right? It's a steel beam, 29,000 KSI. It's the 16 by 31 with a second moment area of about 375 inches to the fourth. And the numerical values we'll get here will all assume one-way slab action, and that we've got the shear tab connection to the columns. In other words, we have a simply supported beam. Or if you want to look at it in a way that would look like your typical textbook problem, here you go. Here's your beam. It's, again, 21.75 feet long, and these loads are applied at the third points, right? And so the tributary modeling would give us then an applied force of 8.845 kips. That's live only, and that's why we don't have the self-weight as a distributed load of the beam in here. And I've left in here this L over 3 symbolically just to emphasize where the 7.25 feet came from. And we have, of course, our two reactions, and with this particular setup, then the numerical value of the reaction is going to be the same as the numerical value for the point load, the two of them that are there. From which then, of course, we draw the shear diagram and we draw the moment diagram. Right? Again, I've left this in both terms of symbolic expression as well as then the numerical value that goes along with this. And I'm going to just rewrite the units again just to make it absolutely crystal clear, because that will be important later. Not kip feet cubed just yet. It's a moment only. We've got the 8.845 kips over here, a rectangle. That's the change in moment. There's 7.25 feet in this span, so that's the change in moment going from 0 to the left. Then that negative value becomes, of course, because we're going right to left, it becomes positive. That would be that increase. There's your 64.1. It's actually, of course, rounded to that. There's some change going on there. Some rounding business there, right? So now we take that moment diagram and we divide by the EI to give us curvature. Right, now we have constant EI all the way along the length. I am not going to put in 375 inches to the fourth. Remember, the 64.1 is kip feet, and I don't want to mess around with converting from kip feet to kip inches and then dividing by a number like 375 inches to the fourth. I'm going to leave it in those symbolic terms. It'll be easier to work with along the way if we do so. Right, we end up with positive moment everywhere. Makes sense given the load that we have imposed, the load model, right? Two point loads acting down is going to cause this beam to want to sag into a concave up fashion, which would be positive bending moment in this smiley face kind of approach here. Now, we could assume for now, and we can derive some other time, that delta max is going to occur at the midspan. Makes sense given the symmetry of everything. Remember, it's not just symmetry of the load, but of the load, the structure. The beam is prismatic, constant EI all the way along the length, and the supports. the supports that are meaningful, right? That we got a pin in a roller, there's no vertical motion here at those two locations. Right? So we're going to go find what the value is of the deflection in the middle, and we can again prove some other time that that's actually where the max displacement happens. But that's what we want. Delta C. Right now, again, we got to classify these problems with the moment area application as one of two problems. Do we know the rotation anywhere? And the answer is no, we don't. So this is of the type where we're going to, of the simply supported type, where we got to figure out what a rotation is first. And we're going to do that in the next part of the video.